All right, seas and oceans part 2. So we're going to continue, and we talked about the geology of the oceans and seas, and now we're going to talk about the water in it and how it's affected by geology. All right, so how do the oceans actually work? This is a pretty important question. So the water circulates, and it has to, right? We have to keep that water circulating. So how does it actually move? So there's going to be a couple different things here, but the first is the Coriolis effect. So our Earth spins, right? It spins in a fairly circular motion around and around and around. All right, and the Coriolis effect is essentially what happens because of this spin. All right, so if the Earth didn't rotate, wind patterns would be incredibly simple. Okay, so the wind would just kind of go from the poles to the equator, back to the poles. But because it rotates, it actually forces the wind to do slightly different things. Oh, my apologies. All right, so the spinning of Earth on its axis forces the atmosphere to deflect wind to the right in the northern hemisphere and to the left in the south. All right, so the further away from the equator you get, the further it's deflected. So right at the equator, there is nothing happening. All right, and what that means is the wind isn't deflected. It just continues in a straight band along the equator. But as soon as you get away from the equator, wind starts to be shifted to the right in the north and to the left in the south. The further away you get from the equator, the more shifted it gets. Deflected is the correct term, but it means shifted. All right? So what happens here is it causes major spirals of ocean circulation patterns. All right? So here are gyres. This is what they look like. All right? And the Coriolis effect is causing this. So the Coriolis effect affects wind patterns, which in turn affects ocean waters. Will this affect all 4 kilometers deep of ocean water? Can the wind penetrate 4 kilometers of ocean water? No, it can't. So now we need to figure out how we circulate deep, deep, deep water. Okay, so the bottom of the ocean. So it deals with density. All right. So which is more dense, cold or hot water? Hopefully by now you feel pretty confident in saying cold water is more dense. All right. Now let's add salt water. Does salt increase or decrease density? Salt increases it. So cold, salty water sinks to the bottom of the ocean. Warm water stays relatively towards the top. All right. This is called thermohaline circulation. Thermo means heat. Haline means salt. So the water in the oceans are circulating based on heat and salt. A single molecule of water can take hundreds to thousands of years to complete a cycle. All right? So the entire ocean takes about 1,500 years to circulate if nothing weird is going on. All right? But water at the poles is cold, it sinks, and that sinking motion causes the entire oceans to shift a little bit. All right? And it moves throughout the entire Earth. The warm water floats on top. As it moves down towards the poles, it gets colder, it sinks. We see that motion kind of forcing the oceans to circulate. All right, so this is what it looks like. We have something that's called density stratification. Density, of course, is something we've been talking about. Stratification just means layers. So we see layers of different density water. Okay, and this is an important thing. If this didn't happen, our oceans would not be doing so well. All right, now this causes something very important. As our cold bottom water, because it's dense, comes to the side of a continent, all right, like the eastern side of South America, for example, it hits this continent, all right, and the motion of the water along with the Coriolis effect forces the cold water to come up the coast where that arrow was coming up. It comes up the coast. Now, this cold water is filled with nutrients like fish poop and other bits of sand and mud and nutrients, all right? Things that phytoplankton, little critters, love to eat, all right? Zooplankton, excuse me. All right? They love to eat it. So as it comes up to the side of this continent, all of a sudden, we see an explosion of diversity because this upwelling is bringing so much nutrients to the surface, all right? So this is how thermohaline circulation and the Coriolis effect work together, all right? So upwelling is essentially both of these put together, all right? And this is really important for you to understand. So anywhere where you have a major fishing industry, It's because of upwelling. So this actually has incredibly important impacts on your life. All right, because the fishing industry is massive. Many of us eat fish across the world. It's a major staple. So this is how it actually works. So if we ever have years where things are unusually warm or cold due to El Nino, for example, this can actually tank the fishing industries. And hopefully you can see why that is. All right, so tides. Tides, so the change in water levels. This is a gravitational attraction between Earth, the moon, and the sun. Okay, and this changes how water reaches the shoreline. So here we have the daily rise and fall of ocean waters. Okay, so here we have the moon and we have Earth. All right, we have high tide and low tide. All right, and you see that high tide happens twice, low tide happens twice in a day. All right, and this changes what time it happens every day. It shifts a little bit. All right, so here we have at midnight, low tide, 6:13 a.m. high tide, noon, low tide, 6:38 a.m. high tide. So you see how it's not happening exactly at the same time every day. All right. So how this works is the moon has a gravitational pull, okay? And the moon is pulling a little bit on Earth. So when it's pulling a little bit, it actually causes a slightly larger bulge of water on one side of the Earth. All right. So that's why high tide happens where it does. Okay. So what you're looking at here are ripple marks. And we can actually track high and low tide in geology through ripple marks made through time. Now, let's talk about the Bay of Fundy. Okay, so this is the bay between New Brunswick and Nova Scotia in Canada, and they have the highest tidal variations in the world. And I'm actually going to send you guys 2 blog posts that I've recently written about the Bay of Fundy so you can learn a little bit more about it. But part of the reason why the Bay of Fundy has the highest tidal variation is look at its shape. We have tons and tons and tons of water moving into that area. All right, we have so much water moving into that area that it just piles up on top of each other, which causes those incredible tides. The most famous places in the world, it moves 100 million tons of water per day. This is at low tide. You can walk around down on the beach. All right, there's some people there. They have to close it pretty suddenly because when the tides come in, they come in rather quickly. It can be very dangerous. All right. And here's at high tide. You can actually kayak through it. And I'll show you a picture of me actually. Well, I won't be in the picture, but I actually took some pictures while I was kayaking through it. So I'll send you guys that blog post. You can learn a little bit more about the geology. All right. You notice the strange shape of those rocks? All right. You see how they kind of narrow out and then they get really fat right at the top? That's because of the water. Water is a very powerful mechanism for breaking down rocks. All right. So coastal processes. Coastal processes like those we see at the Bay of Fundy can drastically change what the geology of an area looks like. All right, so here's 2 very different examples. Which one do you think has higher energy waves? Hopefully you're thinking it's the one on the right. Yes, you can see that. All right, so major things that impact beaches and coastlines are waves, tides, and currents. All right. So we have a couple pieces of vocabulary here. All right, I'm not too terribly worried that you know the difference between swells and ripples and things like that. All right, but we'll just use them a little bit. Okay, so swells are just created from the open ocean from wind. Okay, we call them ripples, swells, and waves. All right, so those are all swells, but they're just different sizes. I'm not terribly concerned you remember the difference between them. Okay. So here are what waves are, wind. All right, so again, that's caused by the Coriolis effect. All right, excuse me. All right, so disturbance creates a larger area for the wind to interact with. All right, so what we're essentially seeing is we're increasing the surface area that this wind can play with. All right, and you can see that increase in surface area when we start to move those waves around. Waves will continue to grow with more and more wind interaction. This is why during storms, waves can get so powerful. All right. Now, wave size is determined by a couple different factors: wind speed, wind duration, and fetch. And fetch is the distance over which the wind blows. So speed, duration, and the distance of the wind blowing. All right. And here's some other terminologies here for you. We have the crest, which is the highest part of the wave. The trough, which is the lowest, the wave height, all right, the wavelength, the distance between 2 waves, just like we learned about in tsunamis, the period, frequency, and wave speed. Okay, so the period is the time required for wave crest at A, right there, to reach B. So it's a timing thing. And frequency is the number of times these crests pass each second. Okay? So it's fairly similar to understanding earthquakes, which should make sense because these are both waves. All right? So they're in a different medium, right? Earthquake waves are just a release of energy. This is water, but they work the exact same way. All right, so crest, highest point, lowest point, trough. Wave height, difference between the crest and the trough. Wavelength, horizontal distance between two crests or two troughs, doesn't matter. Period, time for one full wave to travel. And frequency is the number of waves that pass by a certain point in 1 second. All right, and finally, wave speed is wavelength divided by period. All right, so waves travel in a circular motion, very similar to Rayleigh surface waves in earthquakes, right? So those are body waves, they travel along the surface of Earth, and they travel in a kind of a circular motion. So here is a seabird moving along with the wave. It's easier to see if you have something in the water. All right, so waves interact with water below the surface. You know this if you've ever been to the beach and you've been knocked around by a wave, even if you weren't standing up, you've been under the water. All right, so the depth at which this will interact is called the wave base. Above the wave base, waves will interact. Below the wave base, you won't notice it, okay? The wave base gets less and less and less and less affected the deeper you go, okay? So the interaction surface is about half of the wavelength. So if you take that horizontal wavelength and you divide it by 2, that's about as deep as it's going to affect it, all right? The closer you get to shore, the more percentage of that water will be affected. All right. So as it moves closer to shore, just like in tsunamis, the waves will steepen, right? The amplitude of those waves will steepen. All right. This happens in the exact same way. Of course, with tsunamis, this is caused by shifts of the ocean, of the crustal floor. This is just caused by wind interaction, so it will never be as strong. All right. So this is what it looks like. I don't need you to memorize this chart here. I want you to understand a little bit about what's happening. As the waves come closer to the shore, all right, the wave height increases or the amplitude increases, so the waves will become steeper. If you don't believe me, go to the beach. All right? Once these waves break, they'll come up into what's called the swash zone, and then they will slowly retreat. All right? I'm not going to ask that you know anything about wave crowding, but here it is. Waves interacting with the seabed cause them to slow down. As you can imagine, as we jump up closer to the seafloor, right here, it's going to get shallower, shallower, shallower. We're going to have more interactions. And the sand is actually slowing these waves down. So it's causing them to get more and more closely together. So we'll see the frequency increasing, the number of crests passing through every second. All right, wave steepening. And then finally, we have that surf zone, swash zone, okay? I'm not going to ask that you memorize all these terms. I just want you to understand how waves reach the shore, okay? So I'm not going to ever ask you to define a surf zone or a breaker. All right. This is similar to how seismic waves bend due to changing speeds, okay? So like we talked a little bit about with earthquakes. And what this means is as we reach the shore, waves will actually arrive parallel to the shore even if they came in at a strange angle. Okay? All right. That's wave refraction again. Sorry, I got a little ahead of myself. So again, waves come in at an angle, and they actually come in parallel. All right, so a longshore current. This is created within the surf zone by water moving parallel to shore. So those are longshore currents right here. All right, and it's carrying a number of, or a very large sediment. It's got a fairly high capacity to carry sediment. You'll remember that word from rivers, right? Capacity, the amount of sediment it can carry. All right, so the longshore current's pretty important to understand, especially when we start talking about building on land. And we'll talk more about that in a minute. Now we're going to talk about something you're probably more familiar with, rip currents. You've seen signs warning you about rip currents if you've ever been to the beach. All right, so they're incredibly dangerous, but essentially what happens is when the waves break, they return with their flow and they take essentially a slightly different path and they create incredibly strong currents going perpendicular to the shoreline. All right, So if you ever want to escape a rip current, which you should never try and fight trying to get out of it. You should just swim parallel to the shoreline. You can see if you swim parallel, that's going to be the fastest and easiest way out of it. You never want to try to swim directly towards the shoreline because you're going to be fighting that rip current, and these can be deadly. They kill people every year. All right, so these pose a major threat to inexperienced swimmers and even experienced swimmers. All right, so you never want to go straight towards the shoreline or straight away from the shoreline. You want to go parallel to it. All right, coastal erosion. Water is an incredibly powerful force. It wears away material through abrasion and removal, just like in rivers. You can see this water here has abraded this rock to pieces. All right, so waves will slowly cut away at rocks, just like we saw in the Bay of Fundy. Those rocks are completely cut right here. This is where the water stops. All right, so it can create sea cliffs like this. And here's some sea cliffs on this other side at B. All right, so this is caused by undercutting and sometimes by mass wasting. All right, so we can have mass wasting happening here too. All right, we can also have wave cut platforms, which are these things right here. All right, these are left by low tide and high tide changes. All right, this is where the sea level's retreating, coming back in. All right, so every once in a while we can see weak points in the land close, the land. So this is the headland. This is what we call the headland. All right, so we can have sea arches and sea stacks. So sea arches are things that look like this right here. All right, this is caused by water coming through this area. It was caused by a weak point that's eventually opened up. And finally, we have sea stacks. This has actually been forced away from the actual headland. It used to be attached over here. So remember those Bay of Fundy rocks that you looked at? Those that are sitting out by itself, those are sea stacks. All right, they've been collapsed from the actual headland. All right, so most of the sediment that's produced through coastal erosion is swept out the sea through that longshore current that we talked about. Some is carried along the shoreline and deposited. All right, so here are two examples here. When we build on coasts, we change that erosion pattern drastically. All right, so beaches. I don't need you to memorize what this is, right, the definitions, but it's a gently sloping body of unconsolidated sand, gravel, and shell fragments that we call sediment. Beaches look entirely different depending on where you are. Most beaches have tan colors, all right? So this is created mostly by quartz. So you can see the quartz there in the close-up picture. This is a pretty typical beach color. Some are more whitish, like clear water, all right? This is very clean quartz, sometimes limestone, all right? So an example here is Barbados in the Caribbean at Crane Beach. Some are pink, all right? So this is actually caused by a foram. This is probably Homotrema rubrum, the foram name, you don't need to know that causes this reddish pink color. All right, but these are actually fossils that cause this color. We can have green sands. All right, so green sands are found a lot of the times in Hawaii. This should be a pretty good hint right here. This is an incredibly famous place. You are not allowed to take sand from this area. All right, there's only a couple in the world. There is one in Iceland too, but these are caused by what type of rock? Well, if you're thinking Hawaii was formed by a hot spot and hot spots are formed by mafic magma, then you would be correct. It's mafic. That's olivine, right? Comes right from basalt. All right, so here's Black Sand Beach. This is just another picture of the Hawaiian beaches right there. Still olivine. And then we have Bright Red Sand Beach, right? Here's one in Maui. This is caused by oxidizing iron-rich sediment. All right, so that leads us to barrier islands. Okay, so barrier islands are talked about a lot, especially when we have hurricanes coming. Barrier islands are incredibly important because they're like a self-made defense system against hurricanes, all right? They protect our coasts and our coral reefs from a lot of the hurricane force winds. That being said, they're pretty dangerous to live on in general, right? And what I mean by that is, one, hurricanes, of course, are going to be very strong there. And two, barrier islands are built over years and years and years of erosion. So barrier islands don't stay the same, all right? So they're parallel to the coastline, some distance away from the shore, all right? And there's usually a lagoon between the beach, and on the coast, and this barrier island. All right, so some coastlines are dominated by either erosion or deposition. All right, so erosional ones will have sea cliffs, headlands, sea arches, sea stacks, wave-cut platforms. Depositional ones will look much more calm, so we'll see beaches and bars, sandbars, just like in meandering rivers. Point bars are the same things, all right, and barrier reefs. Which one is which? This one here on the left is the depositional coastline. This one is the erosional coastline. All right. We see a lot of estuaries along the coast. These are caused by rivers and streams emptying into the sea. All right. So estuaries are fairly calm bodies of water that contain a mixture of fresh and salt water caused from streams interacting with the rise and falls of tides. These are incredibly diverse places on Earth. All right. And they're incredibly important to us. They provide a number of advantages to our health as the Earth, as the world. All right. So here we go, some examples of estuarian plants and animals. All right, they have incredible adaptive powers to adapt to ever-changing environments. Now, coastal erosion. This is something that's incredibly important in Florida specifically, okay? And the reason for that is we love building on the coast. However, building on the coast increases the amount of erosion. It makes our land very unstable, and it can destroy a lot of delicate coasts even if it's not necessarily close to where we're building it. Because if we're exceeding erosion, that erosion, the deposition is going to go somewhere, right? So we have some man-made structures, jetties, groins, and breakwaters. All right, here is an example of a jetty. They're man-made walls placed on the inside of inlets, so in the water, to prevent shifting from erosion. All right, so you can see here in cartoon A, here we have our jetties, all right? And you see here that it's kind of preventing the deposition erosion of sand from continuing, all right? It's kind of like a blocker. One of the ways it's been used in the Baltic Sea, it's been used to stabilize bridges, docks, piers, and other things like that, all right? But as you can see, we have a slight issue here. How long is this going to last? Not long. That deposition of sand is piling up, piling up, piling up. So these are not forever fixes. They're short-term fixes. Okay, so now we have groins. Okay, so groins are impermeable, meaning unmovable structures. We move them out perpendicular to shore, all right? They're usually constructed in multiple groups, so we trap and retain sand, which means that the beach isn't starved from sand at each one of these groins. You may have seen something like this if you've ever been to the beach. All right, so as you can imagine, this is going to give us the same issue. Sand piles up to the point where it's unmanageable after some time. All right? All right, and then finally, breakwater. Okay, so here are breakwaters built in parallel to shoreline, and these are protect certain things from the effects of waves and storm surges. So these can protect delicate structures, or it can protect an area that has mass amounts of erosion and longshore drift. All right, but it promotes sand deposition in quiet waters, so they will extend towards the breakwater. That beach will actually extend. You can see that here in A. The beach starts to grow and grow and grow until it will reach this breakwater here. So again, none of these are perfect fixes. So why do we use these techniques? Well, they're cheap, easy, and temporary. They protect man-made structures, and if we can continue to fix them, well, we probably will, because coastal development isn't slowing down. All right, and this is incredibly important because many people want to live on the coast. Many people want a beach house. Many people like going to the beach and doing fun things there. So it's important to know that what will happen if you build your home on the coast. All right, you need to understand that if your coastal development isn't good, this can end in disaster. All right, so building houses can cause more instability. The more instability you have, one, the cost of your flood and home insurance is going to be incredibly high, even higher than Florida is currently. And second, because this can actually become a deadly situation, and it can certainly be a situation where you could lose your home. All right, so what is the other force that acts on coastlines? We've seen a couple of them recently, namely Irma, Florence, Harvey, all right, Maria, and hurricanes. All right, so here are all the hurricanes from 1985 to 2005. They mostly form in the The ones that hit the U.S. generally form right off the coast of Africa, right here, the western coast of Africa. This is where all of our storm systems form. As you can see, they form in other places throughout the world, and they come traveling this way, all right? Hurricanes feed off warmer water. Since we are currently warming our oceans, we are seeing more powerful hurricanes forming. All right, so here are your review questions. I will post this and the blog post for you to read, and I hope you enjoyed this. I will see you guys soon.